Okay, let's see what we can learn about the bias produced by having simultaneous equations in a particular context, a very simple model. It will obviously be much more complicated when we have multivariate regressions, but in a simple univariate regression where we just have one explanatory variable, we'll see that we can say stuff about the bias if we have a model. And this is coming from question 9.5 in chapter 9 in Stock and Watson. So the question says, suppose the demand for commodities given by Q equals beta 0 plus beta 1 P plus U, where U is a random variable denoting other factors that influence the demand curve. The supply for the commodity is given by Q minus gamma 0 plus gamma 1 P plus V, where V is the random factors that determine the price in the supply curve, determine the location of the supply curve. So we suppose that U and V both have mean 0, variances sigma U and sigma squared V, and that they're independent and they're uncorrelated with each other. So we'll first solve the two simultaneous equations to show how Q and P depend on U and V on the random variable. So we have QD equals this and QS equals that, and then in equilibrium QD equals QS, so we can solve. So we set the quantity demanded equals quantity supplied. We have two terms P here, so we bring this one over to the other side and group, and so we have that, and then we bring the beta 0 and the U over to the other side, so we have gamma 0 minus beta 0 plus V minus U on the other side. Now we can divide both sides by the common term there, beta 1 minus gamma 1, so we get P equals, dividing both terms by this. So now we have an expression for P. We can plug it back in to the demand curve. Q equals beta 0 plus beta 1 times P plus U. So we plug in P there. And remember, P has two terms, so that's here and here. So we multiply beta 1 times P, so we get those two terms. We have the beta 0 and we have the U. Now, we have four terms here. 1, 2, 3, 4. Two of the terms have beta 1 minus Y1 in the denominator. So we need to multiply this term by that and divide by that, and multiply this term by that and divide by that, so that then all four terms will have beta 1 minus gamma 1 in the denominator. So we've done that here. 1, 2, 3, 4 terms. We can add them all up, and some of the terms will cancel out, and we'll get Q is equal to this term. So we have P, which I've repeated here, and Q. Now, notice that P is equal to these two terms, which we'll just call A and B. So if we were interested in the variance of the price, that's the variance of term A plus the variance of term B minus, it should be minus 2 times the covariance of A and B. But notice that term A here, these are all just parameters. So A doesn't vary. It's B that has the U and the V that are the random variables here. So B varies. A does not vary. So the variance of A is equal to 0, and the covariance of A and B is equal to 0, because A doesn't vary. So the variance of P is equal to the variance of B, the variance of this term. Now the variance of this term is just the variance of U plus the variance of V multiplied by 1 over the denominator squared. So that's just straight from the definition of variance of a couple of terms. That's chapter 2, chapter 3 in Stock and Watson. Straight application of the definition of variance. It may seem like complicated algebra, but it's actually just an application of the definition. Now we can also calculate the covariance of P and Q. I'm not going to do that. It's a little more tedious algebra, but it's also just straight from the definition of covariance that's given in chapter 3, and you can see that it's going to be equal to this. Now, if you remember from chapter 4 in Stock and Watson, that if we were taking a sample of data, our estimated slope, beta 1 hat, is equal to the covariance divided by the variance. So if we had an x and y, and we wanted to estimate the slope of y equals beta 0 plus beta 1x, we took our sample, we calculated the covariance of x and y and divided by the variance of x. That was our slope parameter in the single variable case. So we can do that. We have the two terms here, and notice that they have common factors, so those two will cancel. So we're left with this as our slope parameter. We're going to do a little bit more math, a little more algebra. I'm going to add beta 1 and subtract beta 1 to the term. So beta 1 hat is equal to beta 1 plus this term, which is the same as that, minus beta 1. We'll see in a second why I do that. Now I'm going to bring beta 1 over to this side, subtracting it. So I have beta 1 minus, beta 1 hat minus beta 1. So that's the so beta 1 hat minus beta 1 is the bias, right? And our estimated coefficient. It's the difference between our estimated coefficient and our true coefficient. So that's going to be equal to what we had before, minus beta 1, and I'm going to multiply beta 1 times 1. But I'm going to use a special kind of 1, which is the denominator here and the numerator, which is the same thing. So this divided by this is just equal to 1, so I'm not changing anything. But now they both have common denominators, both terms, so I can add them up. So when I add them up, a couple of terms cancel out. So this beta 1 sigma v cancels with this beta 1 times sigma v, so that cancels out. So I'm left with sigma u and sigma u here, and multiplied by gamma 1 minus beta 1. So that's what I have here, sigma u, gamma 1 minus beta 1 divided by the sum of the two variances. Now notice the two variances are positive. Variance is always positive. This is a positive variance. This is the slope of the supply curve, which is positive. Beta 1 is the slope of the demand curve, so it's a negative number. So negative times negative is positive. So every term here is positive. So beta 1 hat is minus beta 1 is a positive number. Since beta 1 hat is a negative number, right? Beta 1 hat and beta 1 are negative numbers. That means that beta 1 hat has to be a smaller in absolute value than beta 1. So beta 1 hat has to be smaller in absolute value than beta 1 absolute value. So that's so like beta 1 could be minus 2. So minus 2 minus 3 would be a positive number, right? Because we'd have 3 minus 2 is equal to 1 there. So beta 1 hat in absolute value is smaller, but remember our slope of the demand curve, we invert it because in our demand curve we have price on the y-axis and Q on the x-axis, so we invert the price, so we have, the demand curve, so our slope is actually 1 over beta 1. So if beta 1 hat is smaller in absolute value, that means 1 over beta 1 is bigger in absolute value. So the slope of our demand curve is biased to be too steep. That's what we mean by saying it's biased to be too inelastic. So that's the direction of the bias from the simultaneity, is that it would appear that we have a very steep demand curve when the true demand curve is actually flatter than it is. So in a very simple setting, with a lot of algebra, we can show things like this. And of course, this algebra is just the basis to show more complex general cases, which we might sometimes be interested in.